Welcome for the inaugural talk of a new season of DaSSWeb, our webinar cycle on data science and statistics. And today we have the honor and the pleasure of welcoming Pedro Domingos. Pedro, who perhaps does not need really an introduction, but nonetheless, is Professor Emeritus from the University of Washington in the United States. He's professor in computer science and the author of the bestsellers The Master Algorithm and 2040. Furthermore, Pedro is a winner of the SIGKDD Innovation Award and the IGCAA John McCarthy Award, which are two of the highest honors in data science and artificial intelligence. He's also a fellow of AAAS and AAAI, so the Associations for the Advancement of Science and of Artificial Intelligence. His research covers, in fact, a wide variety of topics in machine learning, artificial intelligence, and data science. He helped start the fields of statistical relational AI, data stream mining, adversarial learning, machine learning for information integration, and influence maximization in social networks. Today, Pedro will present us his recent work on Tensor logic, a simple unification for neural and symbolic AI. Pedro, thank you very much for having accepted our invitation. We're looking forward to hearing from you about the language of AI. The floor is finally yours.
Thanks, Paul, and thanks everyone for being here virtually. What I'd like to do in this talk is propose a new programming language for AI, one that has, I think, for the first time, all the characteristics that you need for it, and hopefully will correspondingly speed up progress. Fields take off when they find their language. Physics took off when Isaac Newton invented calculus, and it wouldn't have taken off without it. Much of electrical engineering wouldn't be possible without complex numbers, or digital circuits without Boolean logic. Chip design builds on HDLs, hardware definition languages, networking on the Internet Protocol, the web on HTML, databases on relational algebra, which we'll touch on a little bit later. And more generally, think of where computer science would be if not for high-level programming languages. A field's language does many important things for it. First and foremost, it saves time. It lets people just focus on the most important things. It makes the key things obvious and puts the others in the background. It focuses the attention of the researchers in the field, and it decreases the entropy. It makes everybody go in the same direction or the same set of directions as opposed to be all over the place. It minimizes the amount of hacking that needs to be done. It unites the field around a set of common concepts, and it changes how people think. So we can ask ourselves, has AI found its language? And one of the first high-level programming languages was Lisp, and it made a lot of symbolic AI possible. And then in the 70s, Prolog took off and became widely used in Europe, Japan, etc. But Lisp and Prolog were not very scalable, and you know they did not support learning very well. And eventually they were overcome by the use of general-purpose languages for AI. In the 90s and 2000s, graphical models for people who do probabilistic AI became a sort of lingua franca that you could do everything in. And then, you know, we developed things like Markov logic networks, which combine the symbolic AI with the probabilistic AI. But there again, the scalability of the inference continued to be a problem. Now, in practice, de facto, these days, the language of AI is Python. But this is actually a very strange thing because Python was never created with AI in mind. And as a result, not surprisingly, is not very well suited to it. It's kind of like it's the wrong set of abstractions, I would argue. Now, of course, it has been extended with things like NumPy, PyTorch, TensorFlow, and so on, which definitely have a lot of great features. But at the end of the day, there's a lot of things about AI that they don't provide. And as a result, you know, people are forced to try to hack those things. Like for example, having the things that Lisp and Prolog did. Now, you know, there is this field of neurosymbolic AI which does try to combine, you know, neural and symbolic AI, and you know, a number of representations have been proposed there. The problem with neurosymbolic AI, painting with a broad brush, though, is that it tends to have, a neural module and the symbolic module, which you then one calls on the other, or you call on them in some way. But at the end of the day, each one of these still has the disadvantages of its own source. So it doesn't quite seem like the right solution. So we can ask ourselves, what should the language of AI do beyond the things that any language should do for its field? And I would say that the first thing is to just hide everything that's not AI. All of the infrastructure, all of the boilerplate, all of the things that are not what we want to focus on should just be in the background. And then it should do things like, for example, easily incorporate knowledge, right? Knowledge in AI is very important. For example, common sense knowledge, domain knowledge, and it should be very straightforward to incorporate them without having to, think a lot about it. And then it should be easy to reason automatically over that knowledge. It should also be easy to learn automatically, which is what things like NumPy and PyTorch and TensorFlow facilitate. It should make the models that are learned transparent, right? In this language, the models that are learned should be understandable and comprehensible by inspection. It should ensure reliability, right? It's one of the main things that a language in computer science is supposed to do, is ensure the reliability of what you do with it. And very importantly, it should scale effortlessly. Now, if you look at this list of desiderata, it jumps out, at least to me, that some of these things Symbolic AI has and has had for a long time. It makes it easy to incorporate knowledge and to reason automatically. In fact, you could say that's what the core of it is all about. The models, like knowledge bases, for example, are naturally transparent, and you can't very much mathematically ensure reliability, so that's all good. But then there's other things like learning automatically, for example, with automatic differentiation, and scaling effortlessly, for example, by automatic implementation on CPUs. These are things that deep learning very much has, and Symbolic AI lacks. So if you really want to have a language that does all the things that AI should do, clearly we need to combine the best of Symbolic AI and deep learning. And the language that I'm going to describe here precisely does that. And what it does is, its starting point is that if you look at what the mathematical foundation of deep learning is, it's tensor algebra. Everything is done by means of tensor algebra plus univariate nonlinearities. Okay? On the other side, Symbolic AI can all be done with logic programming. And so what tensor logic does is it unifies deep learning and Symbolic AI by unifying tensor algebra and logic programming. And I mean unify and not just combine. As we see, what it really does is it makes the two equivalent at a fundamental level, and then it builds up from there. So in order to see how we do that, we first need to look at a little bit of background in logic programming and in tensor algebra. For those of you who are already familiar with these things, I apologize that I'm going to be somewhat informal. The key is just to get the vocabulary and the main ideas down. For those of you who are new to either of these things, of course, this is just the briefest of introductions. So let's start with logic programming. The logic programming is a set of rules and facts. A fact is just a relation applied to a set of objects. So it's a tuple. For example, parent Bob Chris says that Bob is a parent of Chris, and ancestor Alice Bob says that Alice is an ancestor of Bob, and these are two facts. A rule has two parts, the head and the body, and it's written in this slightly odd way, head hyphen body, which should be read as head if body. In more detail, a rule has a consequent, and it has in the body, so the head is the consequent, and the body is a conjunction of antecedents. And so what happens is that if the antecedents are true, then so is the consequent. And the antecedents are just written as a comma-separated list. So for example, the rule ancestor XY if parent XY says that X is a parent of Y for any X in the domain, if X is a parent of Y, so you're somebody's ancestor if you're their parent. Another slightly more interesting rule is that X is an ancestor of Z if there exists a Y such that X is Y's ancestor and Y is Z's parent. So more informally, you're someone's ancestor if there's some person such that you're their ancestor and they are that person's parent. Okay. Now, there are two main logic programming languages, or the two most widely used ones are Prolog and Datalog. In Prolog, the arguments of facts and rules may be constants, variables, or functions. Constants like, for example, Bob and Chris, and variables like X and Y, or functions of these variables and constants. In Datalog, there are no functions. And here we're going to get the functions from a different direction. So when we're going to ignore that part, so we're going to build more on Prolog than on Datalog. Prolog and Datalog and logic programming language in general are interesting in that
Pedro ficou, desculpa.
Sorry, you are muted, Pedro.
Yeah, you are muted, and the screen, you are not sharing anymore. I can see the screen, but you are muted. Right, I see the screen. Sorry.
Can you hear me now?
Yes.
Okay. When did I go silent? What was the last thing you heard me say?
You mentioned Prolog that can have constants, variables, and functions.
Okay, very good. And the other main logic programming language is Datalog. Datalog has no functions. And here we're going to be getting the functions from a different direction. So we're going to more build on Datalog than Prolog. Okay. And logic programming has this interesting characteristic that logic programs can be have both declarative and procedural semantics. For example, a rule can just be read as a statement, as declaring something that we know about the world. But it can also be looked at as a procedure, where the head is the procedure call and the body actually executes the procedure by calling other procedures. Okay, and both of these actually are useful to keep in mind for different things. Now, something important for our purposes is that you can also look at this from the point of view of databases, of database management. In database terms, a rule is a series of joins followed by a projection. The join of two relations is the set of all tuples that you can form from tuples in those two that have the same values of the same arguments. So, for example, here I have two relations given as simple tables, ancestor and parent, including the examples that we saw before. And so, for example, in the first relation, I have the tuple Alice Bob, and in the second, I have the tuple Bob Chris. And notice that the variable y is shared between them, so they join on Bob, forming the triple Alice Bob Chris. Alice Bob also joins with Bob and Dan, which gives us Alice Bob Dan, and Alice and Ed doesn't join with anyone, so it disappears. Okay, so that's the join. The projection of a relation onto a subset of its arguments is the relation that you obtain by throwing away all the arguments that are not part of that subset. So, for example, if from the relation here in this example, can you see me point here? So from the relation,
yes.
So from this relation, if I project onto x and z, y disappears. Okay, and now I just have the shorter relation here on the right hand side. Okay, and you can see that the second ancestor rule here is in the previous slide is the join of ancestor and parent on y followed by projecting out the y. Okay, and this is actually a very useful fact that we're going to make use of going forward. Okay, so how do we do inference in logic programming? There are two main ways. In forward chaining, we start with a set of facts that are the evidence. and we repeatedly apply all the rules in the program until no new facts can be inferred. Okay. In backward chaining, you start with the query, and then you see if the query is a fact. If the answer is in the evidence, we just return it. If not, we look for rules that have that query as the head, and then we repeat the process with their bodies until we find the answer or we can't find the answer. Okay. And which one you use, which one is better, depends on the application. Prolog tends to use Prolog, the standard implementations of Prolog use forward chaining. They use a more general thing called resolution, but for our purposes, it reduces to forward chaining. So we'll just focus on that. Datalog tends to use, and other systems tend to use, Prolog tends to use backward chaining. Datalog tends to use backward chaining. Okay. So for example, if with the rules and the facts that we saw before in the running example that I'm using, we ask, is Alice an ancestor of Chris? Then the answer is yes, because since Alice is an ancestor of Bob and Bob is a parent of Chris, then by the second rule, I get that Alice is an ancestor of Chris. But I can also ask a more interesting question like, who is Alice an ancestor of? Who are her descendants? Which I ask by writing ancestor Alex X. And now, for example, by backward chaining, I can go and try to find all the X's that this would be true for. And if you go through the same, facts and rules in the same way, you get that the answer is Bob and Chris. So Alice is an ancestor of Bob and Chris. Okay. The next question is, how do we do learning in logic programming? And there is this field called inductive logic programming that starts with a database of facts as an input and outputs a logic program that is in some sense a generalization of those facts. And the way it does that is by viewing induction as the inverse of deduction. In deduction, which is what logic programming does as we just saw, we go from general rules to specific facts. In inverse deduction, we do the inverse, meaning we go from specific facts to general rules that would produce them. So the question that the learning system asks is like, what rules would allow me to infer the target predicate, meaning the answers to my questions that are in the training data from the evidence in the training data? Okay. And the search for those rules can be done in a number of ways. It can be greedy search, more often beam search. It is notoriously inefficient, and that's one of the limitations of inductive logic programming. It can be guided by objectives like accuracy, information gain, simplicity, and so on. One very important feature of inductive logic programming is that it makes it very easy to incorporate prior knowledge. We don't have to start from scratch when we learn, as we do with neural networks. We can actually start with potentially already a very large knowledge base that was either written down by people or extracted from text or previously learned from other data sets. And then we just add rules to this knowledge base by the process that we just saw, or refine the rules that we already had there by, for example, adding new conditions and so on. Okay. Now, the search space for inductive logic programming is very large. So most systems that do this have a declarative bias, which means they have some predefined, for example, grammar for what form the rules can take. Okay. And finally, some inductive logic programming systems do what is called predicate invention, which is to discover new relations from the data. Okay? They create rules where some of the predicates in the body did not actually appear in the data, but they infer that those would be useful, for example, because they would lead to a shorter logic program. Okay? So that's inductive logic programming. Now let's do a brief overview of tensor algebra. Neural networks, if you have experience programming them, it all boils down to tensor algebra and univariate nonlinearities. All the things that people do, starting from the most basic ones like dot products and matrix vector products onto more complex tensor operations, are really all forms of tensor algebra, which is nice because it's uniform. So what is a tensor to begin with? A tensor is a generalization of a matrix to a larger number of dimensions. It's defined by its type, which can be real, integer, Boolean, etc., and by its shape. And the shape of a tensor is the number of indices and the number of elements along each index. Okay, and the number of indices is also sometimes called, the rank of the tensor. Okay, and each Each index is sometimes called a mode. So for example, a scalar, a single number, is just a tensor of rank 0. And the vector is a tensor of rank 1, and the matrix is a tensor of rank 2, and now we can have tensors of any rank. Okay? The two main operations in tensor algebra are the tensor sum and the tensor product. So two tensors that have the same shape can be added by having each element of the result be the sum of the two corresponding elements in the inputs. Okay? So an output with a certain value of the indices is the sum of the inputs with the same values of the corresponding indices. Okay? The tensor product can be applied to any two tensors, and each element of the output is the product of two elements of an element of each input and inherits all the indices. So if one input has 2 indices and another one has 4, the result has 6. Okay? And so, we go to each element on each side and do the product. We get a larger tensor, and that's a tensor product. Okay? There are other operations, like, for example, the element-wise product, tensor contraction, all the operations that we know on matrices and vectors. These are all, examples of operations in tensor algebra. A very important fact for our purposes is that these operations are all special cases of what is called Einstein summation. So Einstein notation is something that Einstein invented when he was dealing with tensors to, develop general relativity. At one point, he got tired of having to do a lot of summations over a lot of indices all the time and having the page all cluttered with summation signs. And so he invented this, which he jokingly called his great contribution to mathematics. And Einstein notation is just, let's just drop all the summation signs and establish the convention that implicitly any index in a term that appears repeated will be summed over. Okay? And this sounds very innocent, but is actually incredibly useful. So for example, let's say you want to multiply two matrices A and B. You could just write it as AB. It's nice and compact, but it's ambiguous. You actually don't know what indices are multiplying what, and this works for a few operations on a few indices like matrix multiplication and dot products and things like that. But once you start dealing with more indices and tensors, this becomes very problematic and very error-prone very quickly. You could also write it out explicitly by saying, well, AB is the sum over J of Aij times Bjk, whereas Aij is the Aij element of A, etc., right? This is nice and explicit and unambiguous, but it's also cumbersome. If we use Einstein notation, we drop the sum over J, and we just have what is here on the right, which is Aij Bjk. And the way you read this is, so J appears repeated, so I'm going to implicitly sum over it, and I get back to this expression, but in a much more compact way, okay? So the key message for us here is that everything we do in neural networks can be expressed as Einstein summation, also called Einsum for short, plus univariate nonlinearities, okay? And this Einsum operation is implemented as a library function in NumPy, PyTorch, TensorFlow, etc., although in a somewhat clunky, not very efficient way, and most people don't even know it exists, which is a pity. Einstein summation is incredibly useful, and in fact, if the only thing you get out of this talk is that you should be using Einsum instead of matmul, that's already enough to make it worthwhile. Another thing from TensorLand that will be important for us is tensor decompositions. You're probably familiar with matrix decompositions like the singular value decomposition, which is a generalization to rectangular matrices of the eigen decomposition of a matrix. It decomposes a matrix into the product of three matrices. One, the matrix S is the matrix of singular values. It's a diagonal matrix. The singular values are generalizations of the eigenvalues, and then a product of two other matrices. Okay, and in Einstein notation, this can be written like this: I decompose Mij into SPQ plus a matrix B that transforms the index Q into the index J, and another matrix A that transforms the index P into the index I. So by multiplying by these two matrices, I go from SPQ to Mij. Okay? And now we can ask ourselves, is there a generalization of this to tensors? And the answer is yes. There's more than one. The most useful for us is what's called the Tucker decomposition. And what Tucker decomposition does, if you start from this Einstein version, is actually the generalization to tensors is actually very natural. What you're going to do is, since now you're going to have more indices, because now, instead of 2 dimensions, I have 4, or 2 modes, I have 4, right? I'm going to have more matrices. So for each index in the tensor here, I'm going to have a matrix multiplying it to convert its index into the index of the original tensor. Okay? So if I have, n modes, I'm going to have n matrices. So if you look at this figure here, it shows my data tensor T being to decompose into what is called the core tensor S, and then what are called the factor matrices. So each all the rows in the tensor are multiplied in the core tensor are multiplied by one matrix. All the columns are multiplied by another matrix, and all the tubes, which are the vectors perpendicular to the slide, if you will, those also get multiplied by another matrix. Okay, in this case of a 3-dimensional tensor. So each number actually winds up being part of these 3 multiplications. Okay, and you can think of a tensor decomposition as taking a potentially very large tensor and reducing it to a more compact core tensor. Okay. The data tensor could be very sparse, and the core tensor could be very compact without losing any information, okay, or at least with only a small approximation error. You can also think of a tensor decomposition as embedding the tensor in an embedding space, like multiplication by an embedding matrix embeds a vector. In fact, the tensor decomposition is precisely a generalization of embedding a vector to matrices and tensors of arbitrary rank. Okay. So now that we have the basics down, let's now see what tensor logic is. And tensor logic is based on 2 key ideas, each of which is the answer to a question. And so the first key idea is the answer to the question, what is the relation between tensors and relations? Because symbolic AI does everything with relations, deep learning does everything with tensors. If we don't know how they relate, we can't even get off the ground. Okay. Luckily, the answer to this question is actually surprisingly simple. And the answer is just that a relation and a tensor are essentially the same thing. A relation is just a compact representation of a sparse Boolean tensor. So for example, people in social networks often represent a social network using what is called the sociomatrix, which is a matrix with a row and column for every person in the network, and it has a 1 if they are related, for example, if they're friends, and a 0 if they're not. So for example, in this matrix here, Alice and Bob are friends, Bob and Chris and Bob are then are friends, and nobody else is. So those 3 elements of the matrix are 1, and the rest are 0. Okay? And notice here that the objects in the domain, Alice, Bob, Chris, and Dan, are effectively the indices, or correspond to the indices of that matrix. Okay? Now, the problem with representing this as a matrix is that it's inefficient because it's going to have a lot of zeros, right? Think of the 7 billion by 7 billion matrix of all the friendships of people on Earth, right? It's just really inefficient. So you can do that more compactly by using a relation instead. You can represent this matrix as a set of tuples, in particular tuple Alice Bob, and the tuple Bob Chris, and the tuple Bob Dan. So we just explicitly say what are the indices for which this relation is true, and the others are implicitly 0. Okay? So when you look at a relation like this, you can just see a matrix like this. And this relation happens to be binary, but if the relation had k arguments, now we would have a tensor of rank k, but it would probably be even sparser, so things get exponentially sparser as the dimensionality goes up, but the same principle would still apply. Okay. So now the second key idea comes from the answer to the question, okay, so but then what is the relation between rules and 9 sums? Okay, we just saw that we can do pretty much all of symbolic AI using rules, and we can do pretty much all of deep learning all of neural networks with einsums and univariate nonlinearities. So if we want to unify the two in one language, we need to know what the relation is between them. And again, the answer to this question is remarkably simple. It's just that rules and einsums are also essentially the same thing. Rules are just einsums over Boolean tensors with the step function as the nonlinearity. Why is this the case? Well, think about this. When you actually, let's just look at this example. So let's say we start with the following rule. We have the rule that defines what an ant is. X is Z's ant if X is Y's sister and Y is Z's parent, right? This says that you're somebody's ant if you're the sister of someone and that someone is the other person's parent, okay? And now we know what this rule means in terms of relations and joining them and projecting them as we saw before. But now you can also look at this and say, no, ant is a Boolean matrix, right? Because we just saw you can do that. And so is sister and so is parent, okay? And so what this rule actually is doing is the multiplication of those two Boolean matrices. And now what's going to happen is that when you do one element of the product of sister by parent, if they both have a 1, then the result is a 1, and so you have a 1 in ant, right? So each element in ant is actually going to be a conjunction of the corresponding elements in sister and parent, meaning the result is only going to be 1 if it was 1 in the two inputs, which is exactly what you want, okay? But now if this is a matrix multiplication, you can express it using einsum. I can represent ant by the matrix A, sister by S, and parent by P. And then in einsum notation, AXZ is SXY times PYZ. Notice the common index there, Y, that's the one you're summing over, okay, when you do the dot product, so the matrix multiplication. Now, there's one more thing that you need here, which is the step function, which I'm using the usual notation of H for Heaviside, the Heaviside step function. And this is needed because there's often more than one path by which something could be true, and then you have the disjunction of those, and the result could be greater than 1. The step function just reduces all numbers greater than 1 to 1, so you end up with a Boolean matrix again, okay? But now I can, combining these two things, I could write what I call a tensor equation as follows. And xz, where this is just a matrix in this case, is step of sister xy parent yz. Sister xy parent yz is the product of those two matrices, or equivalently the join of the two relations, right? And the product sign is implicit, okay? Followed by the step function, okay? So all of these three things essentially mean the same. When you look at one of these equations in tensor logic, you can look at it as talking about relations if the tensors are Boolean, but you can also look at it as talking about numbers, right? So these matrices here could be matrices of real numbers, and this would define a matrix product followed by a step function, okay? So these are the two key ideas. So now let's define tensor logic more precisely. So what we do in tensor logic is we define two new operations, tensor projection and tensor join, which are the generalizations to numeric tensors of the database projection and join that we saw before, okay? So the projection of a tensor onto a subset alpha of its indices is the tensor that we get by summing for each value of alpha all the elements that have the values of that index, okay? So for example, you could project a vector onto a scalar by summing all of its elements. You could project a matrix onto a column vector by adding the elements of each row into one element of that vector. You could project a tensor onto one of its faces, and then that face onto one of its edges, and then that face onto one of its corners, which would now just be a scalar. Okay. The tensor join of two tensors on a common subset of indices beta has an element for each pair of elements in the inputs that have the same value of those indices. Okay, so for example, if beta is empty, then this is just the tensor product that we saw before. If beta is all the indices, then it's the element-wise product of the two tensors. Okay, and if the tensors are Boolean, then this is just the database join representing the database as Boolean tensors. Likewise, the tensor projection, when the tensors are Boolean, just reduces, and when you do this and followed by the step function, just reduces to the database projection. Okay, and now a tensor logic program is just a set of tensor equations defined in this way. So a tensor equation is a series of tensor joins followed by a tensor projection onto the left onto the indices in the left-hand side, optionally followed by univariate nonlinearity applied element-wise. Okay. Notice that this is exactly the same form as a rule in a logic program, except that now we're dealing with tensors, and again, the tensors could be real value and so on. Okay. By default, the tensor elements are 0, and so if they're not specified, they're assumed to be 0. And also, equations with the same head are summed, in the same way that rules with the same head in logic programming are implicitly disjoint. And this preserves the correspondence with logic programming and also makes the language more compact. Okay, the tensor types may be left implicit. They may be inferred from the data. Both Prolog, for example, and Datalog on the one hand, and things like Python are not typed languages. But you can also declare them explicitly if you prefer, or if it's more convenient. Now. This is the entire language. The only construct is the tensor equation. There are no keywords, no anything, which is nice because it's very simple and uniform and general and powerful. Having said that, there are a few pieces of syntactic sugar that's, even though they do not add to the expressiveness, are convenient to have just to make things more compact. So, for example, we may want to have more than one term in one equation. So, for example, we can write y is equal to step of wyxi plus c. Right? Why have a separate equation just for the c, right? We can have index functions, like, for example, x of I t plus 1 is equal to wij times xjt, right? So this works exactly as if on the left-hand side we had t as well, except that we increment it. So if we're doing a sequential model, this will be useful. We sometimes want to have functions that are not quite univariate, like, for example, softmax, right? Has a normalization, right? And so we may also want to have that. Also easy to have. So, for example, y I equals softmax of xij means that for each I, we sum over all the j's, right? Because that's the projection part, but then we also softmax over them. So each I is a result of softmaxing over all the ij's that have that I, right? As you can imagine, this will be useful for a bunch of things. There are other tensor functions that we might want to just express as functions for brevity, like, for example, the concatenation of two tensors. We have a matrix ij, and then we want to just concatenate all of the rows into one big row indexed by k. So we can do that. Instead of aggregating by sum, we could aggregate by max or by average, right? Sometimes what we want to do is take the max of the things that we're projecting out, not the sum. Something very useful that Symbolic AI has is procedural attachment. So, for example, in Prolog, if I want to manipulate lists, I could write out some very complicated rules for how to do that, or I can just have a notation for list manipulation, which then is also efficiently implemented more than by using the general backward chaining, and we can have that here as well. And more generally, tensor logic preserves Prolog syntax. So if you want to write Prolog, tensor logic will accept that, because after all, those Prolog rules are just tensor equations. But also, in particular, it will, if you write things in Prolog notation, it will know that you're dealing with Boolean tensors, okay, and so on. So here's a simple example to make things concrete. How do you implement a simple one-layer perceptron in tensor logic? Well, it's basically one line. You write y is equal to step of wixi, okay? The join and project of wi and xi is obviously doing the dot product of them, and then you take the step function, and that's your perceptron. And now you can also give the values of the tensors w and x in the obvious way, right? This is the analog of facts and logic program. You say w is, for example, these 4 real numbers, and x is let's say x is Boolean, x is 0, 1, 1, 0. I can also give x in Prolog notation as x of 1 and x of 2. And what this means is that x of 1 and x of 2 are 1, and the others are 0, which, if that vector is sparse, is very convenient, let alone if you have a sparse matrix or tensor. And then you can just ask the question why by typing y, as you would in either Prolog or Python or other interpreted languages, and then y will get computed as a function of this w and x, and you get the result. Okay, so these 4 lines are the entire program for a perceptron in tensor logic. How would you do a multi-layer perceptron? Well, now the output, instead of just being the left-hand side, instead of just being a scalar, is a matrix where the first index I is over layers, and the second index j is over units in the layer. Okay, and now what we have is in each layer, we have a multiplication of the weight matrix at that layer by the vector of hidden unit values input to that layer, and then we pass this through a nonlinearity like 10H. Okay. Now this is assuming, or this seems to be assuming, that all the layers have the same number of hidden units. But remember that 0 values, unspecified values are implicitly 0, right? So if I just give weights of the if the non-zero weights are of different numbers in different rows, then this one equation implements in different layers. This one equation implements layers of varying size. Or you could also, have a different equation for each layer, which is more cumbersome but more explicit. And it's a matter of taste and convenience. In the same way, you can implement a recurrent neural network as follows. So we have the state of the network is x, and the input is u. So what we have is we multiply at each time step t, we multiply x by its weight matrix w, we multiply u by its weight matrix v, we add the 2, we pass by a nonlinearity, and x the next value of the state vector. Okay, very straightforward, very elegant. One direct consequence of this is that tensor logic is Turing complete. Because as Siegelman and Sontag proved in 1995, RNNs, recursive neural networks, are Turing complete. So if they can be implemented in tensor logic is also Turing complete. Okay. This may puzzle you slightly if you're familiar with logic programming, because DaTaLog is not Turing complete. Prolog is because it has functions, but DaTaLog doesn't have functions. So how come tensor logic is Turing complete? Well, the reason it's Turing complete is that it's getting the functions from a different direction, as I promised earlier. And the way it does this is by the Kolmogorov-Arnold representation theorem, which is a very old theorem that is actually the foundation of neural networks as a universal representation. This theorem says that every multivariate function can be expressed as a sum of univariate ones. A remarkable theorem. Obviously, the tensor algebra gives us the sums. We have the univariate functions by design. So therefore, we can represent any function in tensor logic, and then we also have recursion, like recursive neural networks do. So we have everything that we need for Turing completeness. Okay, which is nice because we do want tensor logic to be a general purpose programming language. Okay, now this is the representation. How do we do inference in tensor logic? Well, by generalizing the forward and backward chaining that we saw before. So we can do forward chaining in the same way that DaTaLog does, and also the RITI algorithm, which is probably the most widely used algorithm for large scale, for very large production systems in symbolic AI. And the way we generalize this to tensor equations is we treat if a tensor program. A tensor logic program is a series of tensor equations. And in forward chaining, we just treat them as linear code. So we execute it in sequence. At each step, we compute the tensor elements whose inputs are available, starting from what was given as input tensors. Okay, and then we repeat this until no new elements can be computed. Okay, and this has the symbolic Boolean version of forward chaining as a special case, as you can probably easily see, right? Forward chaining has the very important property in just the symbolic version, that it's sound and complete, meaning it derives everything that can be derived, and everything it derives is correct, right? Now, this is a really important property in terms of reliability that these symbolic systems have and neural networks don't. But by generalizing it to tensor logic in this way, we're going to inherit, as we will see later, this ability to do sound and complete inference, even when we're working with neural networks and in embedding space, which I think is one of the key benefits of tensor logic. We can also do backward chaining, again, similar to Prolog. What we do now is we treat each tensor equation as a function, okay? And then the query is the top-level call, and then we recurse on this, executing sub-functions and sub-calls and so on, and until we get to the leaves of this process, and then we compute back to the top, and we answer our question, which will be a tensor that is a function of the tensors that were given as inputs and the tensor equations in the program. Okay, and the best choice is going to depend on the application. Next question. How do we learn in tensor logic? Remember, we want to have learning out of the box, like PyTorch and TensorFlow do, and like Lisp and Prolog don't. The thing about autograph or automatic gradient in things like PyTorch is that it's very nice to have, but because the language itself is complicated, right? This is an extension of Python. The auto differentiation is very complicated, right? There's a lot happening under the hood. There's a lot of opportunities for errors and for things to actually be very opaque and so on. And this often leads to problems, when you're implementing things and so on. Now, the good news about tensor logic is that learning is actually going to be, the automatic differentiation is actually going to be very simple, because the only thing we have to differentiate is a tensor equation. And the tensor equation actually has a very simple gradient, as we're about to see. So let's start with a very simple equation: y is equal to ax. Okay, if y is equal to ax, then calculus 101, dy dx is equal to a. Okay, but now think of the equation y is equal to wixi, as you would have in a linear regression or in a singulated perceptron. Now, dy dwy is xi, right? The derivative of y with respect to the ith weight is the ith x, which if you compare with the above, right, this is the exact same equation, except that we just added an index here, y. Okay, so these two things are really the same. Now, even better, this generalizes to when you have y being the product of two matrices m and x. Again, here what we have is that the derivative of the yjth element of y with respect to the ikth element of m is xkj in Einstein notation, right? And right, notice, right, that k, right, is the repeated index here. You're summing over it, and so remarkably, we again have still the same equation that we had before, right? Except that now what we have here is two indices. Here we had zero indices because this was a scalar. Right? This is a scalar. Here we have one indexes because we were computing, a product of two. Sorry, these were scalars that we're multiplying. Here we have one index because we're multiplying two vectors. Now here we have two indices because we're multiplying matrices. But other than that, it's still the same. And more generally, if y is the product of an arbitrary number of arbitrarily shaped tensors, right, or more generally, an arbitrary join of tensors, then the same thing still applies. So, for example, if y is t times x1, x2, xn, etc., then dy dt, and I'm ignoring I'm leaving out the indices here just for clarity, is just going to be the product of the x's, right? The derivative of y with respect to one tensor is just the product of the other tensors. Very, very simple. Okay, so a tensor equation in a tensor logic program just directly maps onto a set of tensor equations that are the gradient, and the gradient of a tensor logic program is itself a tensor logic program with a set of equations that follow from the original one. So specifically, in somewhat loose notation, the derivative of the loss with respect to a tensor is just the sum over all the right-hand sides where the tensor appears of the derivative of the loss with respect to the left-hand side of that equation times the derivative of that left-hand side with respect to the nonlinearity, if it's present, times the product of all the other tensors in the equation, and that's it. Okay? So this is all you need to do automatic differentiation in tensor logic. Now there's an important twist here, which is that in traditional deep learning, every example is backpropagated through a fixed architecture. They all have the same structure. In tensor logic, right, as in logic programming, the structure that you use to answer your question could vary from one example to the next. But fortunately, there's already an algorithm to handle backpropagation in this more general case. It's called backpropagation through structure. And what it does is the following is, my DAG of inference could be different in each example, but as long as I know what the shared parameters are, and I do, right, the weight matrices, for example, then what I do is I compute the gradient with respect to those, and then I add it to my gradient, and then I just do, gradient descent as before, okay? So we just inherit that in tensor logic. Another interesting thing that we can do here is we can do predicate invention, which in inductive logic programming was a pretty complicated and difficult thing, just by Tucker decomposition. Think about it. When you do the Tucker decomposition of a tensor, you actually decompose it into three tensors that were not in the data, but that somehow better capture it. In particular, the core tensor is going to be more compact, okay? And the others map that core tensor to the data tensor. If we do a Tucker decomposition of a tensor in a tensor logic program, right? That Tucker decomposition itself is just a simple equation in tensor logic, as we saw before, and it does predicate invention, okay? And of course, now it does more than predicate invention, because this doesn't just apply to Boolean tensors, it applies to real value tensors and so on, okay? One small piece of bookkeeping is that, so I give you a tensor logic program and say, go ahead and learn it. I give you the interpreter. It needs to know what should be learned. So there are the tensors that are in the data, right? But then, by default, it will learn all the others, but often that's not what you want to do. There are some that you want to keep fixed because they are hyperparameters, or their knowledge that you don't want to change their parameters of the problem. So you need to specify which tensors are to be learned and which are to remain constant, okay? So here's a few more examples of how to do things in tensor logic. Take, for example, a convolutional neural network, right? We already saw how to do a multilayer perceptron. Now, how do you do a convolutional layer? Well, convolutional layer can just be represented by a tensor equation like this. We have a matrix of features, and each feature is over an xy plane. So x and y are indices of pixels in the image. And that is going to be what? It's going to be the image convolved with a filter, right? And so how do we do that? Well, we have to specify the place in the image where we're going to do this, x, y, right? And then the filter itself is a small matrix with elements dx, dy. I add those, right, to the image coordinates. That's how I do the convolution. And then also have a third index here, which is the channel, red, green, or blue. And now I do this tensor join here. I pass by a rel u, for example, and I have my features in the convolutional layer. Okay, very simple. The other thing I need to do is sum pooling. Summing is just projecting out features, right? So I can just do this like this. And if I wanted max pooling, I would have max equal here instead of equals or plus equals, right? One little piece of syntactic sugar that we want to have here is that, remember, when we pool, we only want to take, and if the stride of the pooling is s, we only want to take every s pixel, so we can use the convention. Then when I do x, over s, this is just x mod s, okay? And then I get only those elements, okay? And so this is how we can do a convnet. Here's a slightly more ambitious example. How do we do graph neural networks in tensor logic? Okay. Well, the first thing you need to do to learn a graph neural network is to say what the graph is, right? But we know how to specify a graph, right? A graph is a bunch of pairs. Like, for example, if this was a graph of neighbors, and Alice and Bob are neighbors, and so are Bob and Chris, I can write those out in ordinary, data log notation, and that tells me what the graph is. Okay, very nice and convenient. And then I can easily, change the graph and so on. And now, how do I learn a graph neural network? Well, the first step is initialization, right? And how do I do the initialization? so I'm going to have this tensor of embeddings, which is what the graph neural network runs on, which has three indices: the node, the layer, and the dimension. Okay, so for each node, I have an embedding with some number of dimensions, right? And then I have a series of layers. Okay, and the initialization is just setting the 0th layer to be the embedding of those just the initial embedding of those of all the nodes indexed by n. So x and d just gets copied to embeddings of n0d. Okay, and then this of course will be learned by backup, etc., as we saw before. Okay, meaning the embeddings will be learned by backprop. And now what the neural network does is iterate these operations of aggregation and update. In aggregation, I pull in information from the neighbors. How do I do that? I just multiply the embedding matrix at that layer by the neighborhood relation. Okay, very simple. How does this work exactly? Remember, neighborhood relation can also be seen as a Boolean tensor, or in this case, a Boolean matrix, right? So what I'm doing is just multiplying that Boolean matrix by the embeddings, which precisely zeroes out all the ones that I don't want to have. And only the ones from the neighbors will actually get multiplied and added, thus forming the aggregation. And of course, under the hood, this is all going to be done efficiently so that I'm not going to be wasting time going over zeros, okay? And then in the update, I basically combine that with, the embedding of the node itself using the corresponding weights, pass it by something like a ReLU, and that is the next layer of the graph neural network, okay? And now at the output, let's suppose that I want to do node classification. All I do is multiply the embedding of the last layer, and here I'm using capital L to denote the number of layers. So this is the embedding at the last layer of all the nodes at the last layer, and I multiply that by a vector of output weights run by a softmax, and then the softmax for each node is going to be the softmax over each node is going to be the probability for that class. Okay. And you can do various variations of this that you can probably easily imagine. Let's say you want to do edge completion instead, right? Now what we want to do is predict whether an edge is there for each pair of nodes. And this is going to be the same thing, except that now, or not the same thing, but similar, except that now where I'm going to have the output is not a vector with an element for each node, but a matrix with an element for each pair of nodes. That is the prediction of whether there's an edge there or not. And then what I'm going to do is I'm going to do the join of the embeddings of the two nodes, okay? Followed by something like a sigmoid, okay? And if what I wanted to do instead was graph classification, then this is actually the same as node classification, except that the output, instead of being a vector y with n elements, is just a scalar y, because I just want to produce one class prediction for the entire graph. Okay. Other than that, it's the exact same thing. So what this does is it just does the dot product of the embeddings over all of all the embeddings of all the over all the embeddings of all the nodes. Okay. How about attention? Right. Attention is an important thing these days. Well, the first step of attention is just to compute the query key and value matrices, which of course are just matrix multiplications. And then the actual attention operation is also very straightforward in tensor logic. First, you have to do the comparison, right, of the queries at each. So let me backtrack. So I have here two indices, P and K, right? P is the position, right? So we're going to do this comparison at each position, and K ranges over the indices of the keys and queries. Okay. So what do I need to do? Well, I need to do the dot product of the query at that position with each key, right? And then I have to scale by the square root of the dimension of the keys, right? And then I softmax it. And this is, if you will, the relevance of the key to that query at that position. And then the attention value, the output of the attention head, is just the dot product of this comparison with the value with the vector of values, okay, for each key, okay. So at the end of the day, what is doing is of course a weighted combination of the value vectors where the weights are the softmaxes that are computed earlier. Okay. And since now we know how to do both attention and multi-layer perceptrons, we know how to do a whole transformer. Okay. So I'm not going to go through this in detail, but I think it's interesting to see that you can implement a transformer in tensor logic in just a dozen, fairly short equations, right? Which is a big contrast, I would say, to the enormous complication that implementing a transformer in things like NumPy, in things like PyTorch are. Now, of course, people often say like, "Oh, look, I implemented the transformer in 100 lines of PyTorch," but those 100 lines are really high-level calls to procedures that are completely opaque. And then when you go into those procedures, you actually end up with a lot of code, and that code is often, very, very hairy. Okay. In tensor logic, what you see on the page is your entire definition, and you can see and modify it, very easily. So how does this work? Well, what is my input, right? My input is the text represented as a Boolean matrix of position by token, okay? Or, if you will, as a series of relations, saying like in position 1 I have a token the, in position 2 I have the token dog, etc. And of course, what you do in practice is if you give me a text, it can as a file for input, it can be automatically converted into such a form, right? And then the first thing you do is you embed that, right? How do you embed it? You embed it by multiplying that tensor by the embedding matrix, as you might expect, which is all the embedding vectors for all the tokens. And then you need to do positional encoding, which again is easily defined with a couple equations. This is the one in the original transformer paper. There are others. And then you initialize the residual stream by adding the embedding and the positional encoding. So here, this is the initial. So the stream is the basic tensor that the transform is going to be operating on. It has 3 indices. The first one is the block, right? We're going to have a series of tensor blocks. The second is the position in the text that we're at, and the third is the dimension of the embedding vector. Okay. So notice how this one equation just makes very clear what is going on here. And then we do attention as we saw before, right? We compute we compute the query and etc. Those matrices as we saw, and then at each block and each head we do the computation of the attention again as we saw before. Notice that these two equations are similar to the ones that we have here. What we've done. The only thing we've done is that we've added 2 new indices to the tensor, which are the index of the block and the index of the head, right? And then when you do, forward chaining, this is going to run through them as it's going to run through each block in turn, making things available for the next block and so on. Okay. And notice how easy it was to just take the basic computation of attention and now just put into a transformer just by adding these indices. Okay. And now, of course, we need to, merge the outputs of the heads by concatenation. You need to do layer normalization, and then you need to add that back into a stream, which is another equation. And then finally, the output is just a multi-layer perceptron. And then, of course, you also have the multi-layer perceptrons in each block, which again is a perceptron in the same way that we saw before, but now also indexed by the block, followed by the same addition and normalization that we saw before, or similar, but for the perceptron case. And then the output is just a dot product of the final block value and a set of output weights. Okay, so this is transformers in tensor logic. Okay, or at least the basic transform. Now, but of course, you could now you can go to town. You can do all sorts of variations of this quite easily just by playing around with your tensor equations and adding your things and doing your research. So this is how you do various kinds of neural networks in tensor logic. What about symbolic AI? Well, here the answer is even simpler. If you want to implement some symbolic AI in tensor logic, just write it in Prolog, because tensor logic accepts Prolog. Or if you have it in Prolog, you don't need to do anything. Tensor logic will just carry on with it and now combine it with other constructs, like for example neural network ones as you see fit. And in particular, right, the most interesting and important thing about tensor logic, I would say, is not that you can implement deep networks as we already know them, or symbolic as you already know them, is that you can now combine them and do new things that you couldn't do before, at least that you would have a hard time imagining before. So, for example, you can have embedded databases, right? You can embed your database. How does that work? And then as we'll show, then you can do things with their embedded databases, but one thing at a time. So we already saw that you can embed objects in the standard way using a matrix of object by dimensions. So this embedding for each object, this embedding matrix for each object has a vector of embedding values, right? Now, how would you embed a whole relation instead of just a single object? Well, you can take the relation, right, which you can see both as a relation or as a Boolean matrix, and you multiply it by the embedding vector, or you multiply, you can look at this two ways. You can multiply the embedding matrix by the embedding matrix of each of the arguments, or you can also do this, for each element in turn. But notice what this is, right? This is a Tucker decomposition, right? I have my relation with indices x and y, and then when I multiply by the embedding matrix for I turn this into indices I, into an index I. And the same thing, this one, turns J turns Y into J. Okay. So we can embed a relation just by this one, tensor equation, and what it's really doing effectively is a Tucker decomposition. And embrel, this tensor, the embedded relation, this tensor on the left hand side here, is the core tensor of the relation. So I have my input relation, Boolean, very sparse in general. I multiply it by these two embedding matrices, and which can be the same for the two arguments or different, and I get a core tensor, which is, or in this case, just a core matrix, which is the relation represented in embedding space. Okay, and notice that this important point. This embedding of the relation can be constructed in order of the number of tuples time, right? You don't have to go over all the zero elements, God forbid you have to do that, right? Because the embedding is a linear function of the inputs of the tuples, right? You can just go to all the non-zero tuples, and for each tuple you multiply the embedding vectors of its arguments, and you add that to embrel. Okay, so you just run through the tuples and you produce this compact representation. Okay. You could also embed the relation symbol itself. Often we will want to do that. And one way to do it is to do what is called in logic reifying the database, which is you can turn the relation itself into an argument, and now you just have, instead of x and y as arguments, for example, you have r and x and y. Okay, and you just have this one universal relation called holds, which is, this relation r holds between these objects x and y. Or we can just call it the database relation because it represents the entire database. Okay. And again, if you had relations of varying arities, you could either do this for each one, or you could leave the zeros implicit, and then this is just one, one tensor. And the tensor, by the way, can always be of rank 3 because you can reduce all relations to triples, as RDF does, for example. Okay, so this is actually completely general what I'm showing here. And then you have the embedded database, which again you can see. The embedded database is the Tucker decomposition of the original database, with the embedding matrices as being the factor matrices. Okay, so now we have a database in embedding space, but now the best part, I would say, is that now you can actually do knowledge representation and reasoning based on this idea. Okay, so we've embedded the database. The next thing is to embed rules, right? How do we embed the rules? Well, all we have to do is replace the antecedents and consequents in the rule, in each rule, by their embeddings. So, I'm going to have the embedded consequent being the join, the tensor join, of the embedded antecedents. Okay? And the embedded antecedents were computed just as we saw here. Okay? So the way this works is I start by embedding my query and my evidence, right? I embed my facts, as we saw, I embed my query, and then I reason with the embedded rules, and then I extract the answer. Okay? So I can do reasoning in embedding space with the benefits of both doing things in embedding space, as I will show shortly, but also with the soundness of reasoning in logic. Okay, Now, why does this work, right? You might be thinking, well, okay, this looks nice, but I don't necessarily buy it, right? The reason you can do this is actually that Einstein factors are commutative and associative. Matrix multiplication is not commutative, but when you have an Einstein, it's the indices that determine the order that things get done in. Like whether I put xij before yjk or after doesn't matter, right? The indices are what determines what's going to happen. And so given that, right, let's suppose that, for example, I had my relation, I embedded it, right? And then in this simple case, let's say I don't do, if my inference is just doing a very large number of these tensor products and then projections, right? So just think of one term of this big thing that is, the inference rolled out, right? And this is going to apply to each term, right? At the end of the day, what I have is a relation, things of this form. A relation multiplied by the embedding matrices that I originally embedded it with. Now what I have to do is I'm going to multiply by the transposes to extract the answer, right? More on this in just a second. But here's the key: since these operations are commutative and associative, I can reorder them, and I can multiply just the relation by, for each embedding, the embedding times its transpose. M by x times m by x prime is just the embedding matrix times its transpose. And if the embeddings are random unit vectors, the embedding times its transpose is just approximately the identity matrix. Okay? Why is that? Because the dot product of two random vectors in high dimensions is approximately 0. Okay? This is actually the key property, the second key property they're exploiting here. So what I get here at the end of the day, at the end of this process, is I get back my relations, my original Boolean tensors, plus some noise. But we know how to control that noise by doing various things like increasing the dimension and also using nonlinearities to cancel, to denoise at each step. Okay. Now, but this is actually not the punchline yet. The punchline is that what happens, however, if the embeddings are not random unit vectors, but rather they are learned embeddings, right? That's what we really want to do, right? And once the embeddings are learned, something interesting happens, which is now what I'm going to have is not the identity matrix anymore. It's a similarity matrix between the objects. The ijth element is the similar of this matrix is the similarity of the ith and jth objects as measured by the dot product of their embeddings. So if two objects have similar embeddings as learned, inferences from one will propagate to the other. And the more similar they are, the higher their dot product of their embeddings, the more weight the inferences based on one object will have on the other. Okay? So what this is actually doing is combining symbolic and analogic reasoning in embedding space. Okay? And in particular, if you pass each of these equations through a softmax, right, and they vary the temperature of the softmax, then at low temperature this becomes pure deduction. What this computes is just the deductive closure or the answer to your query using pure, sound, guaranteed, reliable, robust logical inference. Okay. Contrast this with RAG, retrieval augmented generation, where at low temperature all you do is retrieve facts. Here you don't just retrieve facts; you actually produce the deductive closure of those facts, which is exponentially more powerful. Okay. But now, if you increase the temperature, as you increase the temperature, what happens is that more and more dot products, become larger and larger, right? And so you get more and more analogical inferences until, in the limit, everything is similar to everything else and everything follows, okay? So you can actually do this very nice combination of symbolic and analogical reasoning, and you can use the temperature parameter to decide just how reliable and deductive and sound you want to be versus how much generalization and how much generalizing from objects to similar ones you want to do. Okay, so this I think is a very nice combination of the transparency and reliability of symbolic AI with the properties of embeddings in terms of generalization and similarity that are what deep learning is built on. Okay, now I just said, well, I'm doing this analogical reasoning and judging similarity by dot products and so on, which may have reminded you of kernel machines. Okay, And indeed, kernel machines can also be implemented quite straightforwardly in tensor logic. A kernel machine is just defined by this simple equation here, right? At this point, this should be more or less intuitive to you, right? I have, the product over the training instances of their, of the coefficient times the class times the kernel matrix, and then I have a constant, and then the kernel matrix we compute it differently depending on what the kernel is. The polynomial kernel is defined by an equation like this, right? Very simple. For each pair of instances I and I prime, I do the dot product by running over j, and then the nonlinearity here is just raising to the to the power, raising to n, if n is the degree of the polynomial that I want. For a Gaussian kernel, I start by computing for the square differences between all pairs of elements, and then I exponentiate, and then I divide that by the variance and exponentiate, and that's my Gaussian kernel. Okay, very straightforward. And so what this means is that what we were doing with dot products before, now you can also just do with whatever kernels you want, and you can fold elements of kernel machines into the same program. And of course, I would be remiss if I did not mention how graphical models can be implemented in tensor logic. Here again, it's remarkable how simple it winds up being. So graphical models, what is a graphical model? Like a Bayesian network or a Markov network. It's a product of potentials, right? And each potential in the product, for example, in a Bayesian network is the conditional probability of a variable given its parents. This is a tensor, right? So a potential in a graphical model is just a special case of a tensor in the case of a Bayesian network with certain normalization conditions. In the case of a Markov network, it have to be non-negative. Okay, but your potentials are just tensors. And now the two operations that all graphical models use in all inference are marginalization and pointwise product. Right? Marginalization is summing out some variables. Well, this is exactly tensor projection. Right? So when you do projection on a tensor that is a conditional probability, you're marginalizing. And when you and likewise the join is how you implement pointwise product, right? The other main operation in graphical model inference is pointwise product, and pointwise product is exactly just the tensor join as we defined before, applied to two potentials. Okay. Now, of course, just evaluating a tensor logic program as we saw before doesn't necessarily produce correct inference, right? Just as in a graphical model, you get correct inference if your graph is a junction tree, right? And what is a junction tree in tensor logic? In tensor logic, it's just a tree-like program, right? So if your program, instead of being a DAG, is a tree, then just evaluating the program in linear time computes the correct probabilities, okay? So, and then if you want, for example, to compute the probability of a query given the evidence, all you have to do is evaluate the tensor logic program with the query and the evidence as inputs, compute it with just the evidence and divide one by the other. Okay. So specifically to encode the Bayesian network, all you have to do is add a rule for each variable that gives the probability of the variable. So this is a vector with one element for each value of the variable. And this is what is this going to be? It's going to be the join of the tensor that gives the conditional probability of the variable given its parents, multiplied by the marginals of the parents, which are themselves computed by recursive calls on their equations. Okay, and you could even exercise to Derrida do this all as one equation if you wanted to, but it's probably clear this way. Okay, and now the reason that evaluating a tensor program in this way does the correct evidence is something called the sum product theorem. The sum product theorem says that if you have a sum product function, which you can think of as a graph with sums and products as the nodes, and the children of each product node are disjoint, then just by evaluating the network from bottom up, you compute the sum over all the exponentially many states of the sum. Okay, so this is a foundation for efficient inference in graphical models and many other things. And in particular, what this means for tensor logic is if the right-hand side tensors in each tensor equation have disjoint indices, then the tensor logic program computes the correct probabilities in linear time. So just one pass through the tensor program computes the probabilities that you want. If you want to compute all probabilities, as in the junction tree algorithm, they actually need 2 passes, but that's a detail. Okay. Now, of course, most of the time, the graphical models that you want to deal with do not have a small junction tree, so you need to resort to approximate inference methods like loopy belief propagation. What would that mean here? Well, actually, loopy belief propagation is just done by forward chaining if you've expressed your model in tensor logic. Forward chaining precisely repeatedly applies all the equations until they converge, which is what belief propagation does. But if you want to do something like Markov chain Monte Carlo methods instead, what you can do is instead of computing the whole output tensor, right, or sorry, not the whole output tensor, but like every possible path to compute every element of the output tensor, you can just sample those paths. Okay, and we have actually done this, for things like Markov logic networks, and this can be directly transferred to here. Okay, so beyond AI, I would say that tensor logic is potentially useful in a lot of other things. If you think a lot of how a lot of scientific computing works, is what you do is you have a set of equations that you got from a book or from a paper or that you wrote down, and then you want to implement them, right? And then you have to write a bunch of code to do that. In tensor logic, you have pretty much a one-to-one translation between the equations on the page and the code, which is very nice and efficient and transparent. And then generally, if you look at most scientific computing programs, they are these tensor operations wrapped in logic, right? In if, then, this, else, etc., right? And you can do that here in the ways that we saw before. But more importantly, if you want to make the logic learnable, you can just let those tensors, instead of being Boolean ones, just become numeric ones. Okay? And then gradient descent will tell you what the form of the program will learn a program over those tensors. Okay? So more generally, if you have any program, let's say you want to do coding, right? You want to very popular thing to do these days is to use AI for to learn to code, right? If you think about it, like all you have to do, and like what you have to do there with large language models, is translate your language into tensor logic, which you can because tensor logic is Turing complete, right? And then you can make all of those things learnable, right? Then you do your automatic learning over this database of programs, and gradient descent will induce the generalizations of these programs from that. Okay. Now you may be thinking, yeah, this is all very nice, but at the end of the day, it's not going to scale like large language models do. So fun idea, but it's not really going to be widely used. Well, let me just touch on that briefly. There are at least 2 major ways to scale up tensor logic. The first and probably most obvious one is separation of concerns. Tensor logic is all just tensor equations. These are going to operate on a mixture of dense and sparse subtensors, tensors or subtensors, but for example, a Boolean tensor will typically be sparse. You may have dense numeric ones. You can just map the dense subtensors onto GPUs and do those computations there, multiplications, sums, etc. The sparse subtensors, the calculus over sparse subtensors, you handle using a database query engine, which we have decades, of experience in optimizing, right? So the database query engine plays with these, blocks, and then when it comes to combine them using sums of products, you use GPUs, okay? But the second and I would say the most interesting option is actually to do everything on GPUs. We don't even need a database query engine because we can use the Tucker decomposition, as we saw before, to map those sparse Boolean tensors onto dense ones, which now the GPUs are very good for, okay? And of course, to begin with, those dense tensors are exponentially more efficient than the sparse ones, right? We can do that, as I hinted at earlier, with bounded error probability, and if we want to lower the error, we can have a higher embedding dimension, and we can use various other things to limit the error. And maybe best of all, this meshes very well with the embedding and with the learning that we saw before. Okay, so doing this thing actually kills this embedding of the relations. Actually kills a lot of birds with one stone. One of which is scaling up. Okay. Now, even with all of that, of course, establishing a new programming language is a steep hill to climb. Okay, many are proposed and few are adopted. So why would people take up tensor logic when they're so fond of doing things in Python and PyTorch and so on? Well, I think there are various reasons, and also there are various things we can do to help that process. If you think back to why Lisp and Prolog were eventually, superseded by, even for AI, by languages like Java and C++, is that it was a small sub-community, and the network effects of a widely used language just, prevailed over that. But these days, AI is no longer a niche, right? Arguably, AI languages are going to become the general purpose programming languages. So it is often the case that a new language takes off by riding a wave, right? For example, Java became, for a while, probably the most popular language of all because it was the language for networking, and that's what you needed with the internet and so on. Not sure how that exactly panned out, but if you think about today, right, there is an AI wave, and I think tensor logic is potentially the right language for that wave, just like Java was for the internet. Okay. Of course, another very important thing is backward compatibility, right? I don't want to have to throw all my, hard work writing Python code, but I don't have to. In the most basic form, I can just add tensor logic to Python as a better syntax for einsums. But now I can also apply those einsums to do reasoning, which is something that, no one seems to have noticed before. And then little by little, as tensor logic gets extended, it will absorb more and more of the features of Python until maybe you have no particular reason to use it, right? You can start as something that is, interpreted into Python, and then you're still in Python, but at the end of the day, you can just be working natively in tensor logic. And this has happened with other languages before, okay? Now, of course, what really makes people switch to a language is if it cures some big pain they have. And we have those pains in AI today. For example, hallucinations, right, are a very big pain. It really limits the applicability of AI. But tensor logic, in the way that I described before, potentially lets you reason without hallucinations, or at least with a very controlled, very well understood amount of hallucination. And it also lets things be much more transparent, which again, the opacity today of things like LLMs is a really big problem, okay? And of course, language adoption is driven by killer apps. We have those killer apps. Reasoning models are everywhere these days, and they are, I would say, maybe the killer app for tensor logic, but also code, as I just described, math, another popular thing to do, right? You want to be able to do mathematical reasoning, right? A proof is a proof. It's either right or wrong, right? LLMs are not very good for that, or large reasoning models. Who knows what they're going to make up and how you have to fix it. We don't have that anymore. But also, mathematical reasoning is reasoning by analogy, right? As many great mathematicians have said, and we know how to do that here as well. So we have that combination of the rigor and the analogy. And of course, we're going to need to develop IDEs for coding, the data wrangling, modeling, support for the modeler and for the whole, machine learning cycle and so on. But I would argue that tensor logic is potentially a better language for a lot of this than the things that we are now using. Think, for example, of the things that we do, with pandas for data wrangling. I would say that tensor logic is potentially a much more elegant and uniform and generalizable way to do that. We, of course, want to foster an open source community, which will be done in the usual ways. A very good thing to do is to stimulate vendor competition, right? Tell Google that Amazon is doing this, and tell Amazon that Microsoft is doing it, and so forth. That certainly helps if the big players decide to support this. But maybe the most important thing is that I think for education, in many ways, I think one killer app of tensor logic is education. You want to teach AI, modern AI, to students, including both the deep learning, but also the symbolic AI, in a uniform way. And then you want them to do their assignments in the simplest, least cumbersome, least boilerplate kind of way. And tensor logic, lends itself very well to this, much better than the existing frameworks, even before you start worrying about scalability. So that I think is one area where I think, and then very importantly, once people learn how to use a language or whatever system in college or even in school, then they go to their, when they go to work for companies, they bring that along. And this is how a lot of, other things have spread. So the fact that Tensor Logic is potentially so well suited for education also will make it very, will create a very good dynamics in terms of it penetrating into industry. So next steps, I think implementing Tensor Logic directly on top of CUDA is an important one for scalability. And precisely because it's all about tensor equations, the tensor equation maps so well to GPUs, you can optimize the heck out of this. Doing various applications, developing libraries and extensions, but most exciting to me and what I've been spending most of my time on lately is the new research directions that this enables. So to summarize, what I've proposed here is one language for all of AI, a little bit like the one ring to rule them all in the Lord of the Rings. A tensor logic program is a set of tensor equations. Each tensor equation can be seen as a numeric generalization of a data log rule or as an elegant syntax for einsums that applies to both Boolean and numeric tensors. Tensor logic gives you reasoning and learning out of the box. It's transparent and reliable, so don't leave home without it. To find out more, go to tensorlogic.org or scan this barcode that I have here on my screen that will take you there. And thank you, and I will take questions.